The constants of nature are all through physics. So the speed of light, you need that to do electromagnetism, all that kind of stuff. But there are other numbers all hidden throughout the laws of physics, the mass of the electron, etc., etc. So you can't do anything with physics until you know what these numbers are. And the question is, why are these numbers the value that they are?
Welcome, one and all, to the Cool Worlds podcast with me, your host, David Kipping. This time, it is my pleasure to be joined by Geraint Lewis, who is a professor of astrophysics and cosmology at the University of Sydney. Even though he grew up in Wales, the UK, he's now in Australia. He was actually in town in the US, which he's often sometimes in town. I managed to catch him, sit down for a conversation with him this time. And, we know each other scientifically. He's published a huge number of papers, over 500 scientific papers to date, and we have kind of a shared interest in this idea of the weak anthropic principle and its implications for life in the universe, fine-tuning, things like this. So we actually wrote a paper together quite recently on that topic, asking the question, do SETI optimists, or alien optimists you might say, people who think there is life out there, do they have actually a fine-tuning problem when you really dial down to the knobs and dials of the Drake equation and other formulations of how you might think about this problem? So we've worked together most recently, and it was a pleasure to finally have him in town to sit down and talk. Besides from his scientific articles, he's also written 4 books. I've got one of them right here, A Fortunate Universe, Life in a Finely Tuned Universe. And the idea is pretty expansive. The idea that there are many, many constants of nature and other parameters of the universe which appear very selectively tuned, such that if there were anything different, none of us would be here. Not just no humans, but no even atoms, nothing at all. And that has risen the question as to why. Why are all these numbers just right? One possibility is that the universe is just one of many. There's a multiverse out there, and of course we have to live in the universe where all of these constants are correct, because of course we could never emerge in a universe where that was not possible. So that's an example of the weak anthropic principle in effect. And this idea has generated controversy. I mean, there are some scientists who say this isn't even science. We shouldn't be talking about it. This is speculation. It's untestable. So, why are we even including this in science? And then Grant has been, and others have been pushing back on this, saying, look, if you really truly want to understand nature, you can't ignore this problem of fine-tuning, which seems, fairly pointed when you look at these individual cases. It's difficult to make progress if you just keep sweeping this under the rug and saying, don't worry about that. It has to be discussed in a scientific context. So we're going to get into that controversy. We'll dive into some of the pros and cons on this argument, the idea of pauperism, the definition of what science is and is not, and of course talk about where we might even live in this real estate. Are we extremely finely tuned or just finely tuned enough for life? Where do we live in the multiverse real estate? How do we make sense of this multiverse idea? Are there ways to potentially test it down the road? So if you're down for a multiverse conversation and much more, then please do stay tuned. So, Grant, it's a pleasure to have you on the podcast. Thanks for joining me.
Oh, thank you.
So we actually have something in common that a lot of scientists don't share. And I don't want to misspeak here, so correct me if I'm wrong. But, I've been saying for a long time, some of my most popular videos on the channel, on the YouTube channel, Cool Worlds, have been saying, look, we can't be certain that there's life out there, especially intelligent life. We have to be very cautious about this, and we have to concede the possibility. But this seems like a controversial view to have amongst our colleagues, and I think you're one of the few people, correct me if I'm wrong, but I think you're one of the few people who share that view. So maybe you can explain, is that true? Do you feel this way, and why do you feel that way, and do you think it's a controversial opinion to hold?
Yeah, so this is the question of life in the universe is something I've given a lot of thought to. I started coming from a bigger picture of life across the multiverse and the questions of how would a universe be habitable for life? And that gets us thinking about our universe, of course. And when you sort of dig into the question of life in the universe and stars and planets, etc., I've sort of come to the conclusion that if there is intelligent life, right, it has to be rare, because from the way I see it, I think intelligent life would be relatively obvious, if given enough time, that the signatures of intelligent life across the universe should stand out. And so I've sort of come down on the side that I feel that maybe we are the only sort of intelligent life, at least within our pocket of the universe, if not a larger part of the universe. So yes, I have that sort of viewpoint that maybe we're kind of special when it comes to the universe.
Would you extend that not just to intelligent life, but also just to simple life? Where would you land on that?
Simple life, I'm willing to concede that simple life might be relatively common, that there might be many planets with effectively pond scum, etc. on them. But the notion of life developing into intelligent life that broadcasts itself and then starts to travel amongst the stars, I think that side has to be very, very rare.
Yeah, I think there's obviously the evidence-based position which you're coming from. Like, we just don't have any evidence, so why would you conclude that it must be out there? But there's also the sort of the thing I worry about more is the experimenter's bias aspect with this. Just if you go into an experiment convinced, yes, aliens are everywhere, then of course you're going to come back and report that result. You're going to be unconsciously biased in the way you interpret experiments. And we've seen that there's so many experiments or strange results that people have said, oh, that must be aliens. And that's kind of a problem. Aliens is uniquely flexible as a hypothesis. It's kind of like a God of the gaps type explanation. And that personally has always deeply concerned me as an aspect of this. But is that, it sounds like your primary concern is just, I look out, I don't see anything, and so why should we think there's anyone out there?
Yes. So, I mean, it's called the eerie silence, right? The fact that we look out into the universe and we don't see signatures of intelligent civilizations. We don't see communication between the stars or rocket ships flying around, etc. And some people reach for the science fiction defense at this point and say, oh, maybe aliens are so alien that they're doing things that we have yet to imagine, which of course might be the possible reason for this, but in reality we're based in physics, right? And we know that in physics you have electromagnetic waves, etc. They should be signals from civilizations put out there that we can detect, and we've searched across all of the sort of regions of the electromagnetic spectrum, and there's nothing, right? Everything basically falls into the sort of natural bucket. So yeah, for me, the universe is just very quiet.
A lot of people often come from the perspective of the Copernican principle. And this is going to be a good tie-in to actually what you're going to be talking to us later about. We have a seminar after this podcast that you're going to talk about the cosmological principle a little bit, which is closely related. And the Copernican principle basically takes the view that whatever happens here is whatever we see around us is fairly typical, we're fairly normal, we're a typical example. And thus often, and I have very strong opinions about this, as you may have heard them before, about the use of this, but a lot of people do use that and invoke it as therefore an intelligent life must be common elsewhere. So what would be your rebuttal to that?
That the fact that we are here means that we are not necessarily in an average place in the universe, right? There's already the entire question of the rare Earth hypothesis, right? So that our Earth is unlike a typical planet you might find around a typical star, etc. So there might be a whole bunch of coincidences that have led to us being here. But we have to remember that our viewpoint is biased because we are here. And extrapolating to the rest of the universe because we are here is the incorrect thing to do. Really what we should be doing is looking at planets around all the stars and then working out whether or not we're somehow privileged or not with our viewpoint. So, it's a mistake you can make just being here on Earth, right? I mean, I'm here in New York at the moment. I live in Australia. I would be laughed at if I assumed that New York would be exactly like Sydney. There would be similarities, there would be differences. And again, if I was going to go to some random town in the Midwest, again, there will be differences and similarities. But I shouldn't take my particular viewpoint and assume because I have that viewpoint, it is the global viewpoint. And I think this is a mistake people often make. They push essentially the Copernican principle too far. I mean, there are issues in the Copernican principle, stars and planets, which seem to be sort of universal. But then to push that to the notion of life, and intelligent life, I think is pushing it a bit too hard.
Yeah. I often like to say that there are cases where the Copernican principle is useful, and there's cases where it doesn't work. There's clear failings, and you've just given an example there. One of my favorite failings is like an oxygen-rich atmosphere, right?
Yes.
So if you didn't know anything about the solar system, you would reason that all planets must have an oxygen-rich atmosphere, or at least it must be very common.
Yes.
And of course, you'd be very surprised when you found out not only do they not have oxygen-rich atmospheres, they don't often have liquid water on their surfaces, they don't have often very continents or oceans, all this kind of stuff. And you would be startled at how this Copernican principle keeps failing over and over again
Exactly.
when you're trying to apply it. So it does often fail. And I think the reason why it fails is because all of those are statements upon which our existence is predicated. We are only here because there's an oxygen-rich atmosphere. So whenever it's making extrapolations about what's out there, but it's an extrapolation about something which we depend upon, we couldn't survive were it not for that thing, then I think it's a fallacy to use it. But if you're going to use it, and let's say we have a Neptune, and we have a Uranus and a Neptune, pretty similar planets, therefore most solar systems probably have a Neptune. You'd be right, because that has no bearing on our existence,
Yes.
as far as we can tell. And that works pretty well in that case. So I think that's, for me, like the dividing line is, does our history somehow have a dependency on the statement you're making?
Absolutely. And the one I sort of like is this, you mentioned water on the surface of the Earth, right? And we live in a planet which is 70% ocean and 30% land. And if you look at some, when you see artwork of alien planets and they try to draw Earth-like planets, there will be a mix of land and water, etc. But it would be very easy for Earth to have had no water whatsoever, effectively, right? I mean, it depends on the rate the water was brought down.
Like Dune or something.
Yeah, exactly. Or to be a complete water world. And in fact, this is, again, tied to the rare earth hypothesis, this notion that one of the things that's important for the genesis of life is potentially shorelines where you get tides coming in, tides coming out, and you don't get that on a dune, and you don't get that on a complete ocean world. So, as you said, tied to our existence, but we are not 100% sure of all the features of the Earth that are related to our existence. And so again, there's that extra uncertainty in all of that.
So the Copernican principle it's almost like a sibling, I like to think of it, the cosmological principle. They feel like they're closely related to each other. And you have been one of the few people I've seen who's actually been questioning a little bit the use and the validity of the cosmological principle, which is often taken as sort of a fact, right? This must be true, and let's just proceed to make inferences assuming this to be true. So maybe you can just clarify for the audience, what exactly does the cosmological principle say? And where are the places in those statements that you maybe have some questions and concerns?
Yeah. So the cosmological principle, again, sometimes it's not often a robust statement, and you will hear it said in various ways. And essentially, the sort of snappy version is that our universe is homogeneous and isotropic, which essentially means is that what we're assuming is that the patch of the universe that we see is homogeneous and isotropic. It looks the same in all directions. And that's true everywhere in the universe. So if I could randomly plonk myself on another galaxy somewhere else in the universe, I shouldn't expect the view of the universe over there to be radically different to the view of the universe over here,
right,
given that we're observing the universe roughly 14 billion years after the Big Bang. And
so that's the homogeneous aspect, and then the isotropics, like there's no north or south, essentially.
That's right.
Yeah.
That there's no preferred direction. So
Yeah.
you could imagine that you could have essentially a homogeneous view of the universe. But if you imagine that all of the galaxies were aligned in some sense, so there would be a preferred direction. So on Earth, we look at galaxies and they appear to be effectively randomly scattered. And I'm assuming that if I go somewhere else in the universe, I would see essentially the same kind of random scattering of galaxies. So that's a kind of statement, and it sounds almost like a bit of a woolly statement about the universe, but when we would derive the mathematics of our universe, they were based on that assumption. It was based on the notion that there are symmetries in the universe. So this notion of homogeneity and isotropy is that there are symmetries, and you can write symmetries in terms of mathematics, and that feeds into Einstein's theory of relativity, and that's what modern cosmology is built on. But what we have to be very careful of is that the starting point was an assumption, right? We have looked around us and we have said, right, we think this is the way the universe behaves. It's isotropic and homogeneous, and therefore you've built the maths from that. But what if it's not? And there are many ways of breaking that notion of the cosmological principle of homogeneity and isotropy. And you can derive other versions of the space-time structure of our universe where that principle no longer really holds, right? It's a very messy topic because there are many ways of breaking beautiful symmetry, which is what we've assumed. But there are notions that maybe we sit in a deep void in the universe. Maybe we sit in a part of the universe which is somehow underdense compared to the overall average of the universe. And we have been misled by our viewpoint that the rest of the universe might be denser and we're just in this special
So we'd be
point.
a statistical fluke in that case?
Exactly.
Almost? Yeah.
Right. But that statistical fluke has fed all the way through our mathematics into our interpretation of the universe. Or that there could be preferred directions. And there was actually a press release just this week about somebody talking about spins of galaxies as seen with JWST and claiming that there is a preferred orientation. And again, it's small number statistics, but there are people that think that maybe we live in a universe which has that this direction is different to that direction.
Like a chirality almost.
Yes. Yeah. And so that would again mean that the basic assumption underlying our universe is incorrect. And essentially, the flow on from that is that we've got a century's worth of observations of the universe, right? Modern cosmology is almost 100 years old. That we would have to go back and reinterpret because all of our cosmological observations, when we want to work out how bright is something intrinsically, how big is it intrinsically, we use the space-time structure, the Friedman-Lamata, Robertson-Walker metric, as it's called, to derive those observations. But if that isn't really the underlying space-time, then we have to go back to the drawing board, work out what the space-time structure is, and then reinterpret everything that's arrived at our telescopes.
I suppose it's challenging though because intellectually there's far more asymmetrical possibilities, infinitely more asymmetrical possibilities, and there's just one singular symmetric possibility. So it's nice, it's very clean mathematically to do it that way.
It is, but this of course is the curse of physics, right? It's the spherical cow, right? Spherical cows are easy to deal with until you get to deal with a real cow. And as you said, there are an infinite number of ways to distort a sphere from being spherical. And so where do you start, right? So people have gone back to some sort of drawing board, and if you look around, you'll find like Bianchi type 3 cosmologies, where people have tried to derive cosmologies, and you've got cosmologies with voids. They too might just basically be one level of approximation up from perfect symmetry and still be a long way from describing the space-time structure of the universe. And actually this has quite big ramifications. It depends who you talk to, but there are serious cosmologists who essentially look at the use of this simple metric that we use. We use it because it's simple and straightforward. And they basically say, no, we are being fooled. We are being fooled. Our observations are fooling us because we are not interpreting them correctly. And so David Wiltshire, who's at the University of Canterbury in New Zealand, he has something called the timescape cosmology.
Oh, yeah.
Yeah, whereby the space-time structure varies through clusters and voids, and that means that our view of the distant universe, every view is distorted at some level. And his conclusion is that dark energy is essentially a complete mirage, right?
Because we talked about that recently on a Cool Words video, actually. His work,
yeah. So, but of course, we like simplicity, and people stick with what we know, and they will stick with it until you can show that it really doesn't work anymore. But I feel that there's a somewhat growing
appetite for it.
Appetite and interest around the tensions, as they're called, right? We 10, 15 years ago, we were entering the era of precision cosmology. Now we have found things have been so precise that things don't necessarily mesh together. So, there's an appetite.
Yeah, I want to ask you about that. But before we leave the cosmological principle and these symmetries, I want to ask you about evidence on this. So, obviously, there is there are asymmetries in nature. Like there's more matter than antimatter, which
Yes.
is probably the most obvious asymmetry that still sort of defies explanation as to why this should be so.
Yes.
And I think we'll probably connect to our later conversation about fine tuning. So there's certainly examples of asymmetries, but is there any evidence when we look at the CMB or the large scale structure of the universe, do we see any hint of that there could be a preferred direction or preferred local region in which we live?
Yes, and this is what I'll be talking about later today. So there is something known as the cosmic dipole problem, right? Or cosmic dipole tension, I should say. And so, back at the end of the 60s and into the 1970s, this is when we really started to get to grips with the cosmic microwave background radiation, leftover radiation from the Big Bang. And we can see these beautiful maps of the cosmic microwave background radiation, and they tell us that the cosmic microwave background radiation is smooth to 1 part in 10,000. And that 1 part in 10,000, those are the seeds of the galaxies that grew out of the early universe. So that's all well and good. What's less mentioned is that there is a bigger variation in the cosmic microwave background radiation that comes from the fact that we are moving relative to the local expansion. So we have a peculiar velocity. And this was realized relatively early on, but it was measured more accurately as we went through COBE and those telescopes. And
so the CMB has its own rest frame, but that's already somewhat difficult to get your head around because we're often told in relativity that no frames are special, right? But now there is really not necessarily a special frame, but there is a well-defined frame.
There is a well-defined frame, but you can have a well-defined frame with respect to that tree over there, right?
Yeah.
So the CMB, there is a frame in the universe whereby you see the CMB as being homogeneous across the sky. Right, so it's part of the metric that if you are what's known as a co-moving observer, so you are not moving relative to expansion, you see the CMB as being uniform. But if you are not a co-moving observer, if you have velocity due to attraction, due to nearby galaxies, etc., that will be imprinted on our view of the cosmic microwave background radiation. And this has been measured at around 370 kilometers per second. So that's the sun's motion through the cosmic microwave background radiation.
Is there any physical relevancy to that rest frame in terms of like Big Bang, theory? Is this the frame in which the Big Bang occurred in or something? How do we interpret that frame?
It's the frame in which the coordinates are laid down in the Friedman-Robinson-Walker metric, right? So it's related to so again, we assumed essentially that the universe is isotropic and homogeneous, but that's a statement about a privileged set of observers, okay? And so those observers are the co-moving observers, and we shouldn't be surprised that they see the CMB to be isotropic and homogeneous. But all other observers shouldn't see the CMB that way, and we don't. So we are not one of the observers at rest with regards to the universe. So it comes from the fact that we had made that assumption at the start, right? And that assumption, of course, is what basically underpins the mathematics, right? So we have this velocity of 370 kilometers per second. The fact that we have that velocity must mean that all of our other observations of the distant universe must be distorted, right? We will not see the distant universe as being isotropic and homogeneous in any cosmological observation.
So one direction would be more redshifted than the other direction.
Yes.
Yeah.
But there was a really nice test that was written in the 1980s by George Ellis and John Baldwin. And they pointed out that if you do a survey of galaxies, right? So you count in galaxies. So we can do that. You just point your telescope and you count galaxies. In the direction in which we're moving, all those galaxies appear slightly brighter. And the direction from which we're moving, they all appear slightly fainter. Mm-hmm. So if you do counts of galaxies down to some limit, what you'd expect is that we see more galaxies in the direction we're moving in and less behind, right? So this was done in like 1983, 84. And what they pointed out is that this variation across the sky is of order 1% in terms of the counts of galaxies. And back in the 1980s...
Predicted or observed?
Predicted, right?
Okay.
So this is the great thing about theory papers. You always make a theory paper prediction before the data is available to rule your prediction out, right? So that was made in the 80s. We didn't get surveys big enough to start to test this until the end of the 90s. And in reality, it wasn't until the 2020s that we got to surveys of hundreds of thousands into millions of objects. So we could do this kind of test. And this has now been done across a range of wavelengths with a range of surveys. And what people are finding in general is that they find a dipole, as it's called, so we see more in one direction than the other, on the sky, which is aligned with the CMB. Mm-hmm. But the dipole amplitude is too large by around a factor of 2. So if we didn't have the CMB, and we were trying to infer our peculiar velocity relative to expansion from just galaxy counts, we would infer that our velocity is of order 800 to 1,000 kilometers per second. Now, this mismatch between what we see in the CMB and what we see in galaxies is really problematic. For the cosmological principle to hold, they should give exactly the same answer. If they are different, then what that suggests is that there's something different going on with regards to galaxies as opposed to the CMB. And that difference could be that we have extended structure in galaxies that extends over scales, that means that the universe, even when you average it on large scales, is not isotropic and homogeneous. You would still see that this direction is preferred. And it's not just the cosmic dipole that's suggesting that. There are other measurements of what's known as bulk flows. This is like mass movements of galaxies through the universe. They tend to be very extended, they tend to be very large, and they tend to point, again, in a similar kind of direction.
Along the dipole?
Yes. Yeah. So there is this...
So there is a north-south to the universe, essentially.
You know, we're in the realm of, we have statistics that suggest this, but I don't think anybody's going to bet their house on it yet, right? We're at that cusp where we need bigger surveys. We need things like LSST, the Large Synoptic Survey Telescope, to come online to start to give us into the millions of galaxies and millions of supernova, and SKA will be millions of radio galaxies where we can make definitive measurements. But we're at that edge where things are very suspicious.
So, yeah, modern cosmology has many tensions, as you alluded to, and this is obviously one that's emerging a little bit. But I have to mention last week, we're recording this in late March, and the last week we've had a lot of news from DESI we had ACT saying basically everything's fine. This is so they were basically saying the standard model of cosmology, lambda CDM as it's called, works brilliantly. Everything's right in the nose. Don't worry, guys. Don't sweat. And then DESI, the dark energy spectroscopic instrument, I think is they said no, hold on. It looks like this accelerating rate of expansion that is, dark energy is what we often call it. It's not been the same at all times. It seems to be actually weakening over time. So there's a lot, and then of course there's the Hubble tension, which is the fact that if you try to measure this rate of expansion using early tracers of the universe versus modern tracers, you get a different estimate. So it feels like something is happening in cosmology more broadly. There is as you said, there's never been a more exciting time, it feels like, to be a cosmologist. Which do you think these are real, or do you think we are just hitting the limitations of our instrumentation in some way? We are probing the systematics and emerging things out of the machinery that we didn't expect.
I'm not sure if I have a single answer. I'll start by saying that like a year ago, I was at a meeting in London at the Royal Society, and it was basically challenges to the standard cosmological model, right? Now, 20 years ago, that would have been a fringe meeting with a few crazy people in it. But many mainstream cosmologists were there, right? Names you would see on top papers, including Nobel Prize winners, right? And they were discussion. Of course, the big one is the Hubble tension, as you mentioned, right? But there are others, the sigma 8 tension over the clustering of the universe. I mentioned these bulk flows. There's always these constant reports of the biggest things in the universe and questions about whether they're bound, and this dipole tension, etc. So there are people noticing that there are things that aren't quite matching. And of course, as with the DESI results and this suggestion that dark energy is changing, etc. That again is another kind of tension that goes into this. My feeling is that can they all be wrong? Can they all be just pushing up against the limits, or are we really approaching one of those times where something has to give? And I saw this nice little cartoon that somebody had prepared, and the symbol for dark energy is lambda, right? It's the Greek letter lambda, and they basically had the observational surveys pulling on it, saying,
I know the cartoon.
Yeah,
I'll show it for the YouTube audience when it comes up. Yeah,
something has to give, right? And there are people really thinking that something with regards to dark energy, right, which has always been mysterious from, even when Einstein proposed it, but when it came back in the 1990s, it has been and remained mysterious. That something has to give with it. Now, I do know cosmologists who definitely think the thing that will give is the observational surveys, that observers haven't accounted for their systematics and all that kind of thing. A number of these things are very close in terms of their statistical significance. But I think if you talk to a lot of the cosmological observers, their feeling is that it has to be something fundamental with the universe that has to give to put some freedom back in there to account for these various tensions.
Yeah, both camps think the other one's wrong.
Absolutely. Observers don't trust theorists don't trust observers, and it's been that way for a long time. But I think there's a lot of observers out there, right? There's definitely a camp of cosmologists who stand up and fight for the standard cosmological model at every turn. But yeah, as you said, there's a feeling, an appetite, something in the wind that these things are coming thick and fast, and they can't all be consistent, right? They just don't fit together. And so, exactly what's going to give, I wouldn't want to put any money on, but it does feel like an interesting time.
Yeah, and then they're not insignificant. They're not crossing I think maybe the Hubble tension does cross the 5 sigma threshold at this point, but the DESI result, I think, was 3 to 4 sigma.
Yes.
Depending on which sort of how you mix and match the data.
Yeah.
But not at that conventional like Higgs boson was tested, I think, at 5 point something sigma. Yeah. So we're not quite at that point yet, but it would be surprising if over 4 sigma result vanish. That would be a little bit disconcerting about these experiments if something that significant disappear.
And as I said, it's not just that, but expecting all of the 3, 4, 5 sigma things to vanish and everything to fall into some sort of concordance where standard lambda CDM, as it's called, right, cold dark matter, and evolving dark energy, that really is what the universe is doing, and everything else has been somehow flawed in its observations.
So your bet is that probably not all of them are real, but you bet that maybe one of them, or at least one of them, will survive.
I would be surprised if they all disappeared. I wouldn't be surprised if more than one of them was shown to be like actually happening in the universe, right? Because the thing is with all of these cosmological probes is that they're somewhat orthogonal to each other in what they're showing, and so if one is ruled out, that doesn't mean that the others automatically get ruled out, because they're along different axes. So I would be surprised if everything went back to some sort of seemingly normal state that everything was like 10, 15 years ago.
Some people want it to go back to that.
I know, but I think some people just want an easy life. But this, of course, I mean, at the end of the day, this is science, right? And eventually, the evidence has to push you in a certain direction. And you can be a naysayer as much as you want. And I think it was Max Planck who said, science progresses one funeral at a time. Eventually, the community will say, right, this is the way it is, and this is the way we go. As you said, maybe not for 5 sigma, but 10, 20, right? Yeah. And observations will head in that direction.
Yeah, I guess it's a shame that I think reading the DESI paper last night on the plane ride over back to New York, I was flying last night as well, that they were saying that this doesn't help with the Hubble tension. And it's a shame that there is no single idea which would tie up all of these tensions, right? It seems like you're going to have to, if you swallow one, you have to compromise lambda CDM, but it's not going to be one compromise, it's going to be multiple compromises. And I think that's maybe where the theorists have a lot of reluctance here.
So we have to be careful as well with the DESI result. Now, of course, it's an intrepid sort of project, and it's a very important kind of thing that they're doing. But we have to remember that when they talk about this evolving dark energy, they basically explored one kind of model for how dark energy evolves. And so it doesn't necessarily solve the Hubble tension, but if dark energy evolves in a different fashion to the one that they assumed, right? So I think they basically have a linear kind of evolution. It might be something a bit more wiggly. Then there might be more room in that. And there are those that think that, maybe there's a sharp change in what dark energy did at some point, and that might not be observable in the DESI results at the moment, but it might come along later. Now, but I agree with you. I agree with you that I don't think a single fix is going to make all of these tensions go away, because they are across various kinds of observational probes. As you said, fixing the Hubble tension, it's going to be difficult for that to fix, say, the sigma rate or the large distributions of galaxies that people are seeing.
Well, definitely probably be a Nobel Prize if someone did, right? That'd be pretty impressive if someone could turn up.
Yes.
Well, talking about the broadest landscape of cosmology, I want to talk about multiverse and talk about fine tuning. You wrote this book, and I was looking for it this morning. I mentioned I normally like to put the books up here so we can share them. And I loved reading this book, and I was surprised to learn it's about a decade old now.
Yes.
So this is A Fortunate Universe: Life in a Finely Tuned Cosmos, and it really is the book for me which most completely puts together all of the evidence and cases for many dozens of examples of fine-tuning. So maybe you could just, for the sake of the audience, briefly outline what is the fine-tuning argument saying, and maybe give us a couple of examples of this effect.
Okay, so well, firstly, cosmological fine-tuning, as we'll talk about right in a moment, is something that generates a lot of arguments, right? So there's a lot of ifs involved here, so we'll have to just remember that. The important thing to remember is that, of course, physics is a mathematical subject in terms of the theory, right? So when we talk about doing physics, we have the mathematical side, and we compare that to observations and experimentation. And when we derive our laws of physics, it's all good, they're all mathematical, except that the equations themselves are effectively sterile. And what I mean by that is that, let's take like Newton's law of gravity, for example, right? So this is something that's taught in high school. You get the force is equal to, you multiply the masses together, you divide by the distance squared, that gives you the force. Except there's another term in there, which is normally written as a capital G. That is Newton's gravitational constant. Now, the issue is that if you want to use the laws of gravity, right, you need to know what G is. And the only way you can find out what G is by measuring it. And there was a famous experiment by Cavendish way back in the 1700s, 1800s, whereby he measured G. And once you know G, then you can do all kinds of things.
You can't predict G.
You can't predict G. Once you've measured it, you can send rockets to the moon. You can work out how fast an apple will fall, all those kind of things. So once you've measured that number, you're good. And it turns out that these kinds of numbers, the constants of nature, are all through physics. So the speed of light, okay, you need that to do electromagnetism, all that kind of stuff. But there are other numbers all hidden throughout the laws of physics, the mass of the electron, et cetera, et cetera. So you can't do anything with physics until you know what these numbers are. And the question is, why are these numbers the value that they are? Now, some of it, of course, that's trivial, right? Some of it is units, right? So the speed of light we do in meters per second. We can convert it to feet per fortnight if we want to, right? But that's sort of like a trivial kind of aspect. I can make combinations of my constants that have no units, right? So there's a famous number in electromagnetism known as the fine structure constant. It's written as alpha, and it has no units, but it has a value of around 1 over 137. So it doesn't matter how I would measure these numbers in feet or meters, etc. When I bring them together and combine them into the fine structure constant, it should always be 1 over 137.
Mm-hmm.
Why is it 1 over 137?
It's like 42, right?
Exactly.
Yeah.
Now, you might say, oh, it's just some random physicist talking about this, but this is something that Feynman spoke about. Why is it 137? It's one, I think.
Is it a prime number, 137?
Well, good question.
Feels like it could be.
There is a story where I think it was Eddington had been told it was 1 over 137, and he had a theory for why it was precisely 1 over 137. But then he was told that the observations and experiments suggested it was 1 over 138. So then you had a theory for why it's 1 over 138. But it's not an integer. I think it's 1 over 137.15. Yeah. So why is it that value? Why isn't it 1 over 13 or 1 over 13,000? And if it was one of these different values, physics would be different, right? So again, sometimes in terms of raw numbers, things don't really matter so much. But if I'm comparing alpha, which tells me how strong electromagnetism is, to G, which is telling me how strong gravity is.
Which is very weak in comparison, yeah.
These are two numbers that control how a star lives. And so if I imagine a universe where alpha and G are different, then stars would behave differently. Maybe they would burn faster and last 1 million years rather than 1 billion years. Maybe stars don't ignite at all. Maybe there's never enough gravitational squeeze in to ignite the nuclear reactors at the hearts of stars.
Or if you guess, you get black holes everywhere, right? If you made them comparable to each other,
yes,
you wouldn't even have.
If you wind G right up, then matter, instead of collapsing down to form a star, would just keep collapsing, and everything would collapse into black holes. Mm-hmm. So the fine-tuning question is about why our universe has the combination of constants that it does. Because when we look at hypothetical universes where the constants would be different, it is exceedingly easy to make a sterile universe, a dead universe. And it's easy to wipe out any chance of life in a universe. Essentially, the easiest thing to do is wipe out the periodic table, right? Because, I mean, if you think about life and definitions of life, and of course, you run into the science fiction argument again, right? But life is based upon energy and information processing, and you can only do that with complexity. And for us, for humans, that complexity is built into the fact that we are molecular machines. We are built out of an array of 92 natural elements and their isotopes, etc. But again, if I mess around with the strength of the strong force, which is the thing that binds nuclei together, then I can just ensure that things don't stick together. I would have a universe that only has hydrogen in it. And you can't do anything in a universe that has only hydrogen. The periodic table has one element, and your chemistry book has...
So they just never fuse? The hydrogens would never fuse to
Well,
helium?
because they would never stick together, right? So you wouldn't get... You couldn't form even it's just straight out of my head. No.
Deuterium?
Deuterium, that was the word. You wouldn't even form a deuteron, right?
Yeah.
So without that first step, without being able to get those to stick together, then the rest of the periodic table is impossible, right? And so your only chemistry is for two hydrogen atoms to bond into a hydrogen molecule. And that's it. You can't do anything else in that universe.
It's a boring universe.
It's a boring universe. And in fact, you start to mess around with the fundamental constants, right? So our bodies, we're made of protons and neutrons and electrons, right? And so what we have is, due to the relative masses of those, the lowest mass baryon, as it's called, is the proton. And that's the stuff that everything is made of. If you start to mess around with the quark masses, and it's percentage changes here and there, you can actually change...
Which are the constituents of a proton.
The constituents of a proton, the stuff inside a proton. You can change the equivalent of a proton to be a particle known as the delta plus plus particle, right? This is 3 of these up quarks. The delta plus plus looks like a proton, but it has 2 charges on it, okay? That one little particle would still attract electrons, but it would behave like helium. right? And helium, of course, is the most unreactive stuff there is. Helium doesn't join together to give molecules, etc. So what you find is that there are all these routes to shut off things like formation of stars, to shut off the formation of the periodic table. You could have the expansion of the universe be so rapid that just after the Big Bang, there is one hydrogen atom per observable universe.
Just blows apart so
Everything
fast.
blows apart. Or you can flip the sign of dark energy and you get the universe to instantaneously collapse, right? So there's no time for anything to happen. So we end up with this scenario that if you imagine like a volume, right, of the possible kinds of universes that we have, that the vast majority of that volume is dead. And every so often there's a little pocket where there is a universe like our own, where the combination of constants allows there to be complexity and then ultimately life, right? So that's the fine-tuning question: is why does our universe have the values that it does? So that's when you get into the bigger questions of, well, firstly, how do you form universes and how do you give them laws of physics, etc.? And this is where the arguments really start, because there's a theological viewpoint that the properties of our universe were set by a creator that wanted a universe in which life flourishes. But if you want a physical sort of solution without creators and simulations and that kind of things, there's only two real possibilities in my mind. Number one is that there really isn't any freedom in our universe, right? That eventually when we do all of our thinking and get to the ultimate theory of physics, that there's no freedom left. I.e., we will find that the fine structure constant is purely algebraic. It'll be pi to the power of e.
Couldn't be anything else.
Yeah, it couldn't be anything else. Which, in my mind, is a really unsatisfying thing to find, because we've moved fine-tuning somewhere else, right? Because we have mathematics that describe our universe, but the mathematics that describe our universe is just a tiny part of essentially the infinite book of possible mathematics. So why did our universe decide on this set of mathematics rather than something else it could have grabbed off the shelf? The other solution, which I guess is my favored, and just because it's favored more than anything, is this notion of us being part of a multiverse, that there is some process whereby universes are being created, and in that creation process, the laws of physics are written for each universe in some sort of like random fashion, right? There's some stochastic sort of choice that's made, like in the number of dimensions and the mass of the electron, etc. That's set.
Or just fluctuates.
Yes. Yeah. That's sort of set somewhere in the initial part of the universe where things are sort of crystallizing out. And that leads to this notion that hypothetical space of universes that I imagined earlier on is actually a real kind of space of universes, that out there somewhere there is an infinite number, maybe.
So maybe this is a good place to jump in, because there's a couple of different versions of multiverse. Well, many different versions of multiverse. Tegmark actually goes through this kind of classification scheme.
Yes.
But probably most relevant for us is to forget like the Everettian version, stuff like this. I think we're really talking about one I can imagine is if we just go beyond the particle horizon, the horizon, the most distant redshifts we can see, and we just keep going, eventually we will reach some patch where the laws of physics are somehow different. That I find that a little bit difficult to stomach. Like, why should there be a region of this infinitely flat space-time where suddenly laws just look different? But maybe something more easy to stomach would be these are just completely disconnected universes nestled within some hyper space, whatever you want to call it.
Yeah.
Is that more what you have in mind?
That's definitely more what I have in mind. Yeah, so Tegmark's grading of multiverses, right? So the simplest kind of multiverse you can think of is one where actually the laws of physics are the same everywhere, and you go out essentially for forever. And in that universe, of course, you eventually find an arrangement of atoms which are identical to the arrangement here. And so he has that level, whatever, level 0?
Level 1 maybe, yeah.
Level 1, whereby there's an infinite numbers of copies of us doing this kind of interview, but so far away we will never have contact with them. And then there's the idea that you could get this varying laws of physics. But the notion that there is a more general process whereby universes are sort of formed, right? So there's this notion of eternal inflation, which people have spoken about, where there's this background, ever-inflated universe. So inflation is this notion of the very early universe, which underwent this rapid expansion, and that kind of expansion never really stopped everywhere in the universe. It stops in little pockets, and little is like bigger than our observable universe, but we are in one of those pockets. So the locally that inflated expansion ground to a halt, and our universe sort of crystallized out of that.
So if you had a warp drive, you could travel any speed you want. You could, in principle, leave that bubble and eventually encounter this inflationary region again.
That I will say yes, but even though I love warp drives, right, they've only really been the sort of space-time structures only really been calculated in flat space-time, right? So combining space-time structures for inflating universes and warp drives hasn't been done.
Well, don't worry about the method. Just imagine we have some magical way
where we can travel. We'll do magic. Yes,
yeah.
So in that scenario, yes, you would eventually run into this sort of rapidly expanding
which
space
breaks
thing.
the cosmological principle.
Yes.
Right?
Oh, absolutely,
Yeah.
absolutely. But then if you keep going, then you will potentially hit another sort of region of this expanded space-time, which also has come out of inflation, has settled down into its own kind of universe. And again, because of this random nature of how the laws of physics are imprinted, then maybe that patch has a different laws of physics to our own. So the question about whether your warp drive could even exist in that patch, right? Yeah. So if you imagine that you get there and it's only got 2 dimensions of space and 2 dimensions of time, what does that mean for you and your warp drive? Maybe you just keep going and hope to pop out the other side. But yeah, so that's one of the kind of ideas. And there are definitely people that think that because we have this notion of inflation in our universe, in the early part of our universe, that kind of multiverse is inevitable, right? That it has to be like that there are universes beyond our own.
It's an unsettling idea, though. It kind of implies that there is, the breaking of the cosmological principle there actually feels really difficult to stomach, that there could truly be like an end to our universe is difficult to wrap your head around.
Well, there's many things in cosmology that are difficult to wrap your head around, but no, you're right. But then what we're really saying is that the cosmological principle, if it holds, is something that holds just within a region, right? And we know that there's an awful lot of physics that only really holds in a particular region of parameter space, etc. And if you go beyond that, then it doesn't work anymore. So maybe that's the situation we're in.
So in these different universes, so therefore we should not be surprised to live in a universe where we have these constants, because that's just the only place where, to come back to the beginning of this conversation with the Copernican principle,
yes,
we shouldn't be surprised to find ourselves living on a planet with an oxygen-rich atmosphere, because of course we have to live on such a place, and similarly all the constants look that way. Now this is a really controversial idea to some, right? Because many people would say that this is going too far scientifically, that it's making statements about things for which by definition we can never have observations of things outside of our universe. So I want to ask you about this, because I know you've been a defender of the multiverse as a credible scientific notion, but there are many outspoken folks on YouTube and popular science writers and even scientists who say this violates kind of this Karl Popperism. Karl Popper, famous philosopher, who had said something has to be falsifiable, right, to be science, and you can't really falsify the multiverse or even really test it. So, what is your rebuttal to the case that this should be included as a legitimate part of science?
So, you're right. This is something that I have pushed back against because I think that there is I wouldn't say misunderstanding, but there is a fuzziness around discussions of the multiverse, which leads to these kind of arguments, for the sake of a better word. So the issue that I think is the most important is that the multiverse, right, is just a hypothesis. It's a hypothesis that people are putting on the table, right? It's a potential solution to a problem. It's a hypothesis. And in science, you are allowed to put hypotheses on the table. I mean, you can even put ridiculous ones on if you want to, and they will be hopefully ruled out, etc., right?
Irrespective of the testability of the hypothesis.
Well, normally when you propose a hypothesis, you don't know what its testability really is, right? So we talk about the multiverse and other universes, and we make grand statements straight away that therefore these other universes are always out of reach, right? And so we sort of say, right, so it's untestable, and therefore we shouldn't even talk about it, right? Some people say that you shouldn't talk about the multiverse. Yet you get somebody like Roger Penrose who will say to you, oh, I've thought about other universes colliding with our universe and leaving an imprint on the CMB. Right? Now, this is a Nobel Prize winner in physics, right? He is proposing an observation from his hypothesis. People say that observation doesn't hold, so therefore his hypothesis is basically ruled out.
But it is falsifiable.
So it is falsifiable. Until we actually understand what the multiverse hypothesis is in terms of it becoming a theory, mathematics behind it that make predictions, we do not know if those other universes are truly disconnected or not. And you already just said, what if we have a warp drive and can fly there kind of thing, right? As I said, I don't know if we could do that or not. But if we have a warp drive, and warp drives are not ruled out by relativity, right? They might be difficult, but they're not ruled out by relativity. Then maybe those other universes are within grasp. But I think the entire multiverse sort of picture is in such an early stage, really, that you can't really say, oh, it's ruled out just because I don't like it.
So you say it's premature
Yes.
to discount it on the Popperian definition of not being falsifiable.
So my favorite example of this is, and again, pronunciation, people argue about this, but de Broglie, right? So his prediction way back in the 1920s was that, photons, light, can behave as a wave and sometimes as a particle. Therefore, I'm going to say that particles, i.e. electrons, can sometimes behave as waves. Now, did he have any real evidence for this? Not really. But, it was shown to be true through scattering experiments that electrons do behave like waves. Mm-hmm. So he put a hypothesis on the table. It was tested. Nobel Prizes for everybody, right? The multiverse is on the table. It is a hypothesis. It has not been developed into robust mathematics. We do not know what the predictions are going to be. But I would say that the wrong thing to do is to tell people that you can't even talk about the multiverse, right, as a potential solution to problems, essentially because you don't like it, and by making broad statements about what's testable or not until we know what's testable.
But why don't people like it? Is it just that reason they think it's not testable, or is there something? Do you think there's something else going on?
Now I have to put myself in the minds of other people. Some people just don't like the notion. So I've been told that science, the role and goal of science is to understand the physics of this universe, not other universes. Now, that's their definition, right? Other people think it's a cop-out, that people use the multiverse like a get-out-of-jail-free card,
it's
right?
Like a God of the gaps almost.
Yeah, exactly.
It's too powerful.
And so, why is the universe like this? Oh, multiverse, right? But it's not really used that way. Some people might say that they are used that way, but they're just proposing aspects of what the multiverse might solve. They're not answering any questions until the multiverse has been developed into a theory that can be tested, right? I just think it's too premature.
And I guess if you reject the multiverse, you're left with the alternatives, which are not very palatable, right? You have to say either God did it or simulator did it, which doesn't really satisfy anyone, because then you have to say, well, why does God have those parameters anyway? Or why does the simulator live in a universe that's conditioned for life anyway? So you still kind of have the same infinite regression problem. And if you just say it's coincidence, then, well, that's just deeply unsatisfying, isn't it? Just to say it just happens to be so. Don't ask any questions about that. That's kind of almost antithetical to the very way we conduct ourselves as scientists, is to try to explain things.
Yes.
So it has a lot of explanatory power, which feels like the great use of it. It feels also connected to string theory, because string theory, of course, has come under similar criticisms of... maybe it's an example where, similarly, like 20, 30 years ago, maybe more than that, it was first being developed, it wasn't clear that it would be testable. And folks said, give it time, let us work on it. And it turns out, maybe there's still more work to be done there to find a test for it. But it still seems like that's something that never came to fruition, a test of string theory. So do you think it's this version of multiverse discussion is suffering a bit of a sins of the father almost from string theory, that people have looked at what's happened with string theory and are carrying a burden onto multiverse?
Potentially, maybe part of it is because people have grabbed notions from string theory and added it to the multiverse to get this thing called the landscape, right? Where you can talk about individual aspects of string theory, different universes being tied together. Overall, look, I've known about string theory for a long time. So a little story here. When I started my first degree in 1987, I was at Queen Mary and Westfield College in London, and Michael Green was there. And so Michael Green and Schwartz were the fathers of string theory. They wrote those books. And I was told at the time that any day now, string theory is going to have theory of everything. It's all going to be done. Right? We'll just sew physics up and we'll move on. And of course, here we are now, many decades later, 4 decades later almost, and it hasn't come to pass. And you sort of say to yourself, well, so what does that mean? So to me, what that means is that science is actually behaving the way that it should. I think it's good for science now and again to go down a blind alley, because you still learn something in a blind alley. Now, I don't know if string theory or M theory or whatever it's become now is true, is the path to enlightenment or anything. But I think it's possibly wrong to look back on string theory and say, oh, they shouldn't have done this. So, 4 decades of wasted effort, or however you want to call it. Because until you push things to the limit, you don't know where those experimental tests are going to come from.
So what would be the analogy with the multiverse? So you're saying, we need to put some mathematical foundations down for the multiverse, and hopefully come up with a cogent mathematical framework that we can make predictions on what the universes would be like and see how we nestle within this. I guess it's difficult to imagine what that mathematical framework would even look like, because it seems like it can just, what we're really saying is it can do everything. All things can happen. So that it almost seems like an anti-theory, like if it's just allowing for everything to happen.
Oh, well, no. I think you still have to remember that your multiverse theory has to at least produce one universe like this one, right?
Right, but an infinity does do that, right? If you allow everything, monkeys on a typewriter, you will get us in one of those.
Yes.
So that I guess what I'm saying is your multiverse theory could be as simple as that. It could just be let everything that's possible be possible. And that's your entire mathematical framework.
Yes. But then you've got to explore, well, what's the consequences of that? And if your theory is that our universe is truly disconnected and will never to have any influence from the surrounding universes, etc., then that's it. That's as far as it's gone, really, right? What you would hope, though, is that somebody else says, oh, no. Actually, it would look like this. I have a slightly different theory whereby it can't produce an infinite number of different kinds of universes. It produces some sort of set, and within that set, there is at least one universe that looks like this one. So this one is also a contender. And then you would look in there, right, are there any other consequences for that theory as opposed to the, consequences on our universe from the existence of other universes, right? In the Bayesian framework, right? So essentially, you would favor the one that has less universes in it compared to one that can do everything, right? So you would sort of say, well, this is more preferred than the other one. So
Yeah.
I think the fact that we inhabit a universe is evidence that you can put into multiverse theories and use. It's going to be very sloppy until we have robust predictions, but we have to remember that our universe has to be in there somewhere.
So there was a mathematical idea I came across with Multiverse that I wanted to mention. I'm not sure if you're familiar with this piece. It was in 2023 in Nature Astronomy by Zhuwei Wang and Sam Braunstein. And they argued, I kind of like this argument. They actually sent it to me, and I think they wanted me to talk about it on the Cool Words channel, which maybe I one day will. I just haven't kind of got around to that, but I think it's a cool idea. They argued that we're more likely to live on the shores. Imagine, there's all these sterile universes out there in this landscape of multiverses, and there's some islands of habitability where the parameters are just right, and you could maybe tune them by 1% in every direction, and that's your island of habitability. And they argued that we're more likely to live on the shore of that island than in the center. And the argument was essentially that when you think about a hyperdimensional sphere or cube, the surface area is actually very large compared to the volume. So an example would be if you have a two-dimensional sphere, then 1 minus 0.9 squared, which is 19% of the points, lie within 5% of the boundary. But if you go up to, let's say, a 20-dimensional sphere, or say a 50-dimensional sphere, that's 1 minus 0.9 to the power of 50.
Yeah.
So that's now 99.5% of the points now lie. So if you have 50 tuning parameters, the vast majority of the volume actually lives on the boundary.
Yeah.
And that was a really intriguing idea to me. So maybe, and we kind of think about this with exoplanets, we often think the Earth is sort of this ultimate habitable planet, but others have been suggesting maybe there are super habitable planets out there which are actually more habitable than us, or more well suited for life than us. And this almost feels like a multiverse version of that argument, that we may be barely habitable. Is there any, I guess that might be a point where you could actually ask that question more pointedly with a mathematical framework. Could we make the universe more suited for life if we changed any of these numbers, or do we seem to live at the absolute precipice of how you would choose those numbers?
Oh, well, talking about making the universe more habitable is a difficult thing to do. My co-author Luke and I have chatted quite a bit about this, and you can imagine universes. So we already mentioned things like the strength of the strong force and the strength of the electromagnetic force, and they're different by, I think it's 10 to the 6 orders of magnitude. But you can imagine a universe where they're very similar, right? So in that kind of universe, you pop a cake in the oven and you turn on the oven and you bring it out and it's turned into lead, because you can do alchemy, essentially. You can do nuclear physics at the energies of electromagnetism, which is what you use when you're cooking. Is that going to be a more habitable universe? Maybe it is. Maybe life would be able to use nuclear sort of reactions, the way that we use we use electromagnetic reactions now. Similarly, messing around with the periodic table. I mentioned it's very easy to wipe out the periodic table, but what if you made the periodic table more stable, and you made extra heavy elements, and you made extra stable isotopes, right? So imagine that there were 50 versions of carbon to use. You could probably build a lot more complexity out of that. So it could be that you could have a more habitable universe, but defining habitability, I think, is trickier. Are we at the edge? Again, it's kind of hard to say, right? Because it's hard, this definition of what is a habitable universe.
Yeah, I guess, are there any numbers which seem precariously like you don't have much leeway to play around with them?
Well, there are some that have very, very narrow bands, right? So there's the famous one, which is the resonance of the carbon nucleus, etc. They appear to have narrow bands, but are we near an edge of that? It's kind of hard to say. The problem, so part of the problem is that a lot of the focus of all of physics has been on the physics of this universe. So we have measured things in this universe, but we haven't measured what goes on in large numbers of hypothetical universes. And in hypothetical universes, you can vary one constant and play a little bit, but in reality, you want to watch the entire evolution of that universe to try and understand, if I change the electron mass, how does that change the distribution of galaxies, etc. That's a lot of work to do, and people haven't explored that. The one I think people have looked at is the question of the amount of dark energy we have in the universe. This is work that Luke and I and several others did a few years ago, where we generated other universes with larger amounts of dark energy, which makes
change the cosmological constant?
Yes. Yeah, change the cosmological constant. So acceleration takes over earlier and earlier. So in our universe, it took over around 5-6 billion years ago. But if you increase the amount of it, eventually you push that back earlier and earlier. And what you find is that shuts down galaxy formation faster and faster. And what we find is that, you can make the cosmological constant maybe 100 times larger, and you still end up with things that look like galaxies, right? But are they habitable galaxies? Well, we don't know. They're smaller. They have a lot of gas in them. They probably form a lot of stars. They probably go through a lot of, generations of stars very quickly. Lots of supernova in a small volume are not good for life. So we've shown that the cosmological constant might be larger and allow galaxies to form, but is that enough to say that those universes are more habitable or even habitable at all? So we need to delve into the physics of what goes on inside the individual objects before we say, well, where's the boundary with the cosmological constant and life?
But if you go to 1,000, you probably don't even have galaxies, do you?
No, things basically empty out very, very quickly.
So I guess you could almost have like a conservative upper limit, but you're never sure of the true how far you can squeeze it down.
Yeah. And of course, the other problem that you're talking about being within 5% of a boundary, and we're talking about the density of the cosmological constant, etc. But is that the right parameter that we should be looking at? Because these things feed into equations in different ways, and if it's really the log of this quantity or the square of this quantity, etc., the distribution changes, and where you are in that distribution also changes. So it's a complicated, multi-dimensional thing that we haven't gotten to grips with yet. This is one of the things, is the entire fine-tuning thing, is that there is so much potential volume to explore, to understand the impact of change in a constant on the overall evolution of a universe.
Yeah, so it sounds like in your opinion, the current the sheer number of these coincidences demands invoking a multiverse essentially at this point. There's really no satisfying alternative.
To me.
Yeah.
To me. But I think to other people, I think they would find some other way to satisfy themselves.
So this is obviously one of the many books you've written. I want to highlight you've been a prolific author, and you've written many of the works. So where can people find, if they want to learn more about your writings, where can they go to? Well,
the books are available on Amazon, so you can just search for me there. I actually have 4 books on there at the moment. I have a 5th book, which is currently, I need to do some more editing on it, but it hopefully will appear by the end of the year. It's on the nature of reality. It'll be called The Shortest History of Reality. We talk about physicists' view of what reality is there. I have a rather frozen website that I really need to update, geraintflewis.com. But there's a place on there. I'm always happy to answer people's questions and chat about cosmology and physics. So if people have questions, they can contact me there. And last year, of course, I moved from X to Blue Sky. So I'm also happy to talk about physics there too.
Yeah, and of course you're a great lecturer. I've seen you you've done the Royal Institution, and of course you've been on Veritasium numerous times. So you're easy to find on YouTube as well in many different places, including here now finally on the Cool Worlds podcast. So thank you so much for joining me today, Grant. This is great.
Thank you very much.
So that was my conversation with Geraint Lewis. I hope you enjoyed it as much as I did. These kind of conversations are always real head scratchers. I don't think I'm ever going to have a satisfying answer to this fine-tuning problem. Fine-tuning has so many aspects, not just, of course, in a cosmological sense, which we're mostly focused on in that conversation, but as we kind of alluded to, it also exists even thinking about the Earth and the rare Earth hypothesis. And of course, Ward and Brownlee brought that up, year 2000, I think that was their famous book, The Rare Earth Hypothesis. And it has been a constant topic of discussion and controversy whenever you look at ourselves, be it our universe, our planet, even humanity, and try to ask questions about what it means for what else might be out there. Because, proponents will say, this is the data we have to work with it. And critics will say, we are completely biased by having this one data point, and so we shouldn't even attempt to learn anything from it. But there is something strange here. I mean, when you look at, certainly in a cosmological sense, all those parameters being so finely tuned, it does demand an answer. And I'm not satisfied with the multiverse answer. I have certainly been thinking about it a lot recently. And, many nights in bed, I've been kind of awake thinking like this is not very satisfying. We need a better answer to this than what we have, but it's not really obvious what else you would invoke. Hopefully, I think that the dream scenario would be that one day we would come up with some kind of unified, glorious theory that would explain all of these constants, all of these numbers, and we could all just rest and go to sleep. But certainly for now, we seem to be a very long way away from that point. And, I think cosmology is such an active field. We keep hearing of all these tensions and crises of things not agreeing with our theories right now. So it feels like we're at a crossroads. There are problems like the fine-tuning, but there's also problems in our observations. There are lots of things which are pushing on our standard ideas, our standard models of how the universe works. And that's kind of exciting. It's exciting to live in a time when it feels like there's something new just around the corner. We are waiting for that next Einstein, I guess, to come along and reveal to us some deeper insights about the universe. Or at least I hope someone like that or a team of such people could come along and reveal that to us. So very exciting times, intriguing questions, and I hope you're enjoying learning about all of these questions and thoughts and ideas. So if you want to support what we do here on the Cool Worlds Lab podcast, the best way to do that, of course, is, you can just hit the subscribe button on YouTube or follow us on Spotify. And if you have the means and you think we deserve it, you can also head to our website, coolworldslab.com/support. That's coolworldslab.com/support, where you can become a regular donor to my research team, the Cool Worlds Lab, where we are investigating and publishing on these types of questions that we talked about today and much, much more. So if that sounds of interest to you, please do head to our website. And as always, I hope you have a great one out there, and I'll see you in the next episode.